We'll be looking at Oblivious Transfer, which is a technology that involves sending data such that only a part of it will arrive, and the sender doesn't know which part will actually arrive. It will be the receiver choosing what they can read. To give you an example to illustrate it is a problem where you want to know who has the most money. No one wants to brag about how much money they have, but they've decided that the richest person needs to pay the bill for dinner. So now you want to compare who has the highest amount of money, but you don't want to reveal to the others how much money you have. So they all run a multi-party computation protocol where they input their amount of money, and the protocol will spit out the winner, the person with the most money, but it won't reveal to anyone involved how much money anyone has. That's a sort of application that you could do with Oblivious Transfer. But let's first talk about Oblivious Transfer itself. The most basic protocol is called 1 out of 2 Oblivious Transfer. I'm thinking of 2 values. Now in this case, I can think of the 2 values of these 2 cards. Now obviously you don't know what these values are, but I know what they are, right? Now, you're not supposed to know this, but this card is the 7 of diamonds and this card is the 9 of spades. But you don't know this, right? I'm putting them here and I want you to read the value of one of these cards, but you don't want me to know which one of the 2 cards you've read, right? So you're thinking of a bit 0 corresponding to this card, the 7 of diamonds, bit 1 corresponding to this card, the 9 of spades, and I'm not supposed to know which card you're thinking of. So I give you these 2 cards, and then you open one and look at them while I'm not looking at what you're doing, right? Mm-hmm. So now you know either the 7 of diamonds or the 9 of spades. I don't know which one you know, but you know one of them and you don't know the other, right? So that's the sort of physical example of it. But how do we do this with cryptography? How do we do this electronically? Right? We might naively think, why don't I just encrypt the 2 values? I just encrypt 7 of diamonds with key 0 and 9 of spades with key 1. And then you can ask me for key 0 or key 1. But if you do that, I will know whether you were thinking of 0 or of 1. So that doesn't work. What if I give you both keys, key 0 and key 1?
Then I can look at both.
Then you can look at both. Yeah. So that's also broken, right? We have 2 requirements, which is I can rely on the fact that you can only read 1 card, and you can rely on the fact that you can read at least 1 card after your choice. So in order to do this, we can modify RSA a little bit to accomplish this. And this is the sort of most well-known 1 out of 2 Oblivious Transfer. So let's refresh our memory on what RSA is. There's a video that I did about this topic. We don't need to know all the details. There's really only one important fact that we need to know. So RSA works in the modular world. So to remind ourselves, if we have a number x mod, let's say 12, what this means is that we divide the number x by 12, and we are only interested in the remainder of that. In other words, if we have a clock with 12 hours and it's 15 hours, well, 15 divided by 12 is 1 with a remainder of 3. And it's the remainder we're interested in, right? So all the values we'll ever see will be between 0 and 11. Because we're computer scientists, we like to include 0 there. So instead of 1 to 12, it will be 0 to 11. Now RSA works in this modular world as well, but instead of having a small number like 12, we have a big number, n. And n is a really, really big number. Like 1,000 bits nowadays is already considered to be not enough. You know, every once in a while, n will have to go up as our computational power gets bigger. But let's say that n is 1,024 bits, right? So then you have a massive number, n, and you're doing your mathematics modulo n. Then the special property that we have for RSA is that there are 2 values, e and d, such that if you take x to the power e to the power d, this is equal to x modulo n. Now, how this property is created, you'll have to look at the RSA video, obviously. we have to just accept this as a fact for Oblivious Transfer. So one party, say Alice, can generate E, D, and N such that this property here, that desirable property, holds. Now, how can we use this property for Oblivious Transfer? I'll draw something called a message sequence chart to explain the protocol. So we have two parties involved, Alice and Bob. We're drawing a line here and here, and this allows us to sort of visualize the communication between the two parties. If we draw something for Alice on the left or for Bob on the right, so on the outside, it means that it's their private information that they're not sending. And if we draw an arrow from Alice to Bob or from Bob to Alice, it means that they're communicating this information to the other party. So Alice starts off with two hidden messages. So let's call them message 0 and message 1. In the example before, message 0 was 7 of diamonds, and message 1 was the 9 of spades, right? And now Alice wants to communicate this to Bob, but only one at a time. So the first thing she does is she creates a public-private key pair in RSA, right? So she generates the N, the E, and the D with the property that we just discussed. She keeps the D a secret, that's her private key, and she sends N and E to Bob. That's the public key part. N and E are sent to Bob. The next thing she does is she sends two completely random values to Bob. These are values smaller than big N, but generally quite large random values. Let's call them x0 and x1. So these are just random numbers that Bob will receive. Now Bob, before anything started, thought of a bit, right? He wants to read either the top card or the bottom card. So he selects which card he wants to read and call that bit B. So that's a value he's thinking of. Now after he receives the two messages x0 and x1, he will select a value, xb, right? So if he's thinking of 0, he will select x0, and if he's thinking of 1, he will select x1. So after Bob receives x0 and x1, he selects a random key k. Then with that key k, which is a secret for Bob, he does the following computation. He takes xb plus k to the power e, all of that modulo n. He can do that because he was given e by Alice, so he knows that value. He was given n, so he knows that value. K is a value that he randomly selected, and so is b. xb is simply one of these two values depending on the value of x. So he can compute this, and that value, that's a single value, let's call that value v. What Alice can do is she can take the value v and privately compute two versions. The first one is p0, which is equal to the formula she just got, which is v minus x0 to the power d. Similarly, p1 is equal to v minus x1 to the power d. So again, this is something that Alice can compute because she's given the value v. She knows the values x0 and x1 because she created them and sent them to Bob. And she knows the value d. So she can simply compute p0 and p1. Now, the final step is where the magic happens. She sends two values to Bob, which is m prime 0, which is defined to be m0 plus p0 mod n. And the other value is called m prime 1, which is equal to m1 plus p1, also mod n. And this allows Bob to then do the final step, which is to compute m star, which is equal to m prime of the bit he chose, minus k plus pb. And what it turns out is that this value m star is equal to mb. And that's exactly what we want, right? So Bob, at the end of the protocol, now knows mb. So to illustrate this protocol, let's go with the bit that you selected, right? You selected the bottom card, which was bit 1. So we have B is equal to 1. And we fill in this value for the protocol. So M0 is going to be filled in as the 7 of diamonds, and M1 is going to be filled in as the 9 of spades. I'm then thinking of some crypto values. We're not going to instantiate those, and similarly for the random values. It doesn't need to be this complicated. What is important here is that XB here is of course going to be X1. So V will equal X1 plus K to the E mod N. Then I will compute P0 and P1. So what will P0 be and what will P1 be? Let's start with P1 because that's the interesting case. So P1 will be the value V. What is the value V? Well, okay. P1 is V minus X1, all of that to the power D. Now we can instantiate V because we know now, because you chose bit 1, that it's X1 plus K to the power E. So this is equal to X1 plus K to the power E, which is the value for V, minus X1. All of that to the power D. Now obviously X1 minus X1 cancels out. So what we're left with is K to the power E to the power D mod N. And that's the whole magic of RSA. K to the power E to the power D was equal to K mod N. Right, so it nicely cancels out, and what we're left over is the value K. So P1 is equal to K. Now for P0, this isn't going to work. We're not going to do the math for P0 because it's not going to lead anywhere, right? Because the value V is X1 plus K to the power E, and if we then subtract X0 and raise that to the power D, it's not going to have any nice properties. So let's ignore that for now. So P1 has the nice property that is equal to K, and P0 does not have this property. Now if we look at the final computation here, we see that M prime 0 is going to be M0 plus P0. That doesn't have any nice properties, because P0 doesn't have any nice properties. But M prime 1 has nice properties, because it's going to be equal to, let's work this out, M prime 1 is equal to M1 plus P1. P1 is equal to K. So that means that this is equal to M1 minus K. If we then look at the definition of M star is equal to M1 minus K plus K, which is equal to M1. And that's exactly what we wanted. So this is how Oblivious Transfer works. Now the other question is, how do I know that you can't read the other bit of information? I'm not going to go into the technical details here, but remember that the definition of P0 was just some random formula to the power D. If you can work out any random thing to the power D, then you can actually break RSA. So the whole point of RSA is that you can't work out a random number to the power D unless you know D, which you don't. So that's where that comes from. There's a lot of technical details that are very interesting, but that don't fit into this video. So now we have 1 out of 2 Oblivious Transfer. How can we get, more interesting versions of Oblivious Transfer? Let's first, instead of thinking about small pieces of information, like a single card, what if I want to send you a file? RSA only allows small messages because our messages M0 and M1 have to be in the domain of N. Right? If they're bigger than N, they definitely can't work. And N is at 1024 bits. So any message longer than a kilobyte, we're not going to be able to do this. What we can do, however, is we can take 2 files, file 0, and encrypt it with a symmetric key S0. And we can take file F1 and encrypt it with symmetric key S1. I'm now going to send you both encrypted files, and I'm going to now run the Oblivious transfers on the symmetric key. So you will only know the symmetric key of file 0 or the symmetric key of file 1, depending on your chosen bit. And I don't know which chosen bit that is. So that is how we can send entire files using Oblivious Transfer. And now the final step, which is 1 out of n. 1 out of n Oblivious Transfer. So what is the trick here? So we'll do 1 out of 4 Oblivious Transfer as an example, and after that it will be, I think, quite clear how we can generalize this to n. So what we do, instead of having 2 files encrypted with symmetric keys, we're going to have 4 files now, and based on your choice you can read only one of those files and I won't know which file it is. So the first file, we're going to call it file 00 for the binary notation of a 2-bit 0. So file 00 is going to be encrypted with S upper 0 lower 0. And all of that will be encrypted again, so there's 2 layers of encryption with S upper 1 lower 0. And we do this for the next file, F01, which will be encrypted. The inner key, so that's S upper 0, is going to be 0 again, because the first bit is 0. But the outer key this time will be S1, because it's the outer key, but then the subscript here will be 1, because this bit is 1. Similarly, the next up will be file 10, which will be encrypted by S0. It's going to be 1, because the inner bit is 1, and the outer bit is 0. The same is true for the fourth file. In this case, both the inner and the outer key will have bit 0. So now we can do a little tree of Oblivious Transfer. So I do an Oblivious Transfer, and you're going to either select inner key 0 or inner key 1. So that will be S0, 0 on one side and S0, 1 on the other. I won't know which of the 2 bits you've selected. And that means that I don't know which one of the 2 symmetric keys you've selected. And then we do the same for the outer key. So you either select at your will S10 or S11. And this is true in both cases. So that means that at the end you've made 2 choices for 2 bits, and this allows you to then have a pair of symmetric keys. Let's say that you went for 0, 1, so that means that your inner key is 0 and your outer key is 1. So that means that you have the following keys. You have keys S00 and you have the key S11. And you can now decrypt file 01. And you don't have S10, so you cannot decrypt this. You can't decrypt this because you don't have S01. And here you also can't decrypt it because, again, you're missing one of the 2 keys. Of course, you can now, instead of having a tree of depth 2, you can have a tree of depth 3 or 4 or 5. And this means that with logarithmically many Oblivious Transfers, I can make you select 1 out of any number. If you then want to select k out of any number, I can simply run the protocol k times. Is that the best way of doing it? No. But it's a way of doing it. So of course there's a lot of technical details and a lot of optimizations to be had. But I think it's really cool that I can send you some information that you can only read a part of, but I don't know which part. So the applications of this, we've mentioned multi-party computation. So here, I want to go into more details about this later. So there's a particular protocol called garbled circuits, which is extremely powerful. It allows you to run any arbitrary logic over any arbitrary input without any of the parties learning any of the input. It's very powerful and very cool. But there are other things you can do with this. Another one is private information retrieval. So let's say that I'm a data storage and you don't want the people making the queries don't want the data storage to learn what they are interested in, right? Simply the metadata of people keep accessing the same file might in itself be a privacy violation. So there are some interesting ideas surrounding there as well. This is one of the worst things that can happen. So instead of using a single input, we need to use two inputs. The other input being
again. Sean, maybe you can tell me reasons why G3 should be more similar to G1, and maybe reasons that it should be more similar to G2.